First we are seeing some general concepts in the organic chemistry. So, the first topic is hybridization, and due to the hybridization how the carbon is making the sigma and the other type pi bonds. So, let us take one example like a methane molecule. So, here it is observed that the carbon is making the 4 bonds with the hydrogens. So, let us see how the carbon and the hydrogen is making the bond formation, for which the bond angles and bond lengths, the stabilities and all that we have to understand, for which we will go into the chemistry of this carbon, how many electrons are available, what is the electronic configuration and which electrons are actually forming, that is involving in the bond formation. In the bond formation, is it the strong bond, that is sigma bond, or it is a weak bond, that is pi bond? All such things we have to explain under this particular topic. So, let us take the under the hybridization, we have first type of hybridization is sp3 hybridization. To explain this one, the carbon electronic configuration we are taking, the carbon atomic number is 6, that means 6 electrons are there. They are arranged in the first shell 2 electrons in the orbital s orbital. In the second shell we have 2s2, 2p2, totally 6 electrons only, but this electrons we too can show that there are 2 electrons paired up. In the p orbital px, py, pz, there are 2 electrons are available in the p orbital, but the how many electrons are used in the bond formation? 4 bonds, that means 4 electrons are required. Generally what understood is the unpaired electrons are responsible for the bond formation. How many electrons are available? Only 2. So, therefore, this is considered as only the ground state electronic configuration, and this is not helpful to explain this type of the tetravalency or the 4 bonds formation. So, therefore, we propose one more electronic configuration. The carbon takes some energy available in the surroundings and goes to a next electronic configuration, that is called excited electronic configuration, in which 1s2 will be the intact, but one of the electron excites from this place to the next one. So, therefore, the s orbital will have only 1 electron. In the p orbital we have 3 electrons. So, therefore, now we are showing, so 4 unpaired electrons are available now. So, the question like the carbon in the electronic configuration only 2 unpaired electrons, how it is able to make the 4 bonds, means we have to say in the excited electronic configuration there are 4 unpaired electrons are there, thereby it is able to make the 4 bonds. But we have to consider one more thing, s orbital is a spherical type of the orbital, whereas the p orbitals are, one will be in the x axis dumbbell shape, one will be in the y axis again dumbbell shape, and one more pz orbital will be like this, half will be towards our side, half will be the back side, which may be written like this, okay, on the dotted line we are showing. So, px, py, pz, these are all dumbbell shaped orbitals. S orbital is round shaped, those their shapes are different, and their energetically also s orbital is little lower energy, more stable than the p orbitals. Therefore, resulting these 4 bonds also should not be identical, should not be identical, but what is the found is all the 4 bonds are identical. So, the first question, how come this tetravalency is explained by the excited state and involvement of these 4 electrons. Now, another question is, how come this identical orbitals, means the theory shows that all these 4 electrons are going to be merged, the process called now hybridization we are proposing. In this hybridization, before the that is participation, these 4 electrons, 1 s orbital and the 3 p orbitals are going to combine, or the process called the mixing process, in which 4 identical orbitals, called them as sp3 hybrid orbitals. Each hybrid orbital, they will be neither will be like spherical nor will be the dumbbell. Their shapes are described as one small lobe and one big lobe, right. How many orbitals are produced? 4 such orbitals are formed. These 4 will be better shown like this. One orbital will be one side, the other 3 will be like this. So, all the 4 orbitals are 4 sides in fact. In fact, in the hybridization theory shows that if the 2 hybrid orbitals are there, one will be east side, one will be west side. The theory shows that the hybrid orbitals want to be separated maximum angle. So, when 2 hybrid orbitals are there, the angle of separation will be 180. The shape will be just like line they are making. So, therefore, it is described as linear shape when only 2 hybrid orbitals are formed. When 3 hybrid orbitals are formed, all the 3 will be 3 sides 3 occupying the 3 sides, having the maximum bond angle, that is 120, 120, 120, 120 total 360, right. So, what will be the shape of these 3 orbitals together is a trigonal planar also. So, they are plane and 3 sides 3. If 4 are there, can you expect what will be the shape? Means somebody can expect like this. So, east and west, north and south type, that is 4 sides 4 orbitals making a square planar. But here the angles are in between these 2 is 90, in between opposite is 180. This is not correct. Hybrid orbitals want to be the equal and the identical with reference to the others. So, therefore, this is not the most destabilized one. Instead, if you cut this into 2 halves, one you rotate opposite to this one, then you will get another shape called what? A tetrahedral shape. In that shape, imagine that there is a tripod having one candle, right. Now, this legs, if it is expanded, it comes to a situation like this, 3 sides 3 legs and one will be candle. Now, you measure the bond angle between any of these 2 will be the identical between the either 2 legs or leg and the candle. This type of symmetry is called what? Tetrahedral. Why you are calling tetrahedral means the area occupied by the 3 legs is actually triangular. With reference to this, if you construct a prism, there will be 3 faces and 1 ground face. Total 4 face symmetry is formed, which is identical in all respects. Therefore, it is called as a tetrahedral symmetry. So, therefore, if 2 hybrid orbitals are there, it is going to be linear. If 3 hybrid orbitals are there, trigonal planar. If 4 are there, not the square planar but tetrahedral. In the tetrahedral, one will be up just like a candle on the tripod, 3 will be acting as the legs. Now, between the 2 legs and the leg and the candle, the angle will be same, that is 109 degrees 28 minutes. Either between the 2 legs or leg and the candle identical. So, now all the orbitals will have the identical shape, identical bond angles, identical energies and so on. Such 4 orbitals, if they combined with the 4 hydrogens, that is nothing but the 1s1 electron in the hydrogen. So, now you will have a 1 sp3 orbital of the, this is sp3 orbital of the carbon, with the hydrogen 1 sigma bond is formed. Like that 4 sides 4 the hydrogens will be making the 4 bonds. This is nothing but a methane molecule. So, if a question comes, explain how the methane molecule is formed, means you have to start from the carbon original, that is ground state electronic configuration. Say there are only 2 unpaired electrons are available. These 2 are not enough to make the 4 bonds. Therefore, we have switched over to another electronic configuration called excited state, in which we have a problem. S will be the lower energy, higher energy, shapes are different. So therefore a theory is proposed called hybridization theory, in which before bond formation they will merge into the identical type of the 4. How many are participating? 4. So equal number of hybrid orbitals are formed. The name of the hybrid orbitals also 1s3p, therefore sp3 hybrid orbitals are formed. How many are formed? 4. All will be identical, having neither will be spherical nor will be dumbbell, but spherically dumbbell. If you close this one, it is spherical, but being the 2 lobes is the dumbbell quality. So it is, you can say, spherically dumbbell orbital. 4 are formed. That 4 will be like this. 1 will be up, 3 will be down type, and the symmetry is described as tetrahedral. These 4 hybrid orbitals, if they are allowed with the overlapping of the hydrogen 1 electron, 4 sides 4 bonds are formed between the 2 hydrogens. Now if you write like this, it looks like only 90-90, but actually the methane molecule will be 1 hydrogen up and the 3 hydrogens will be like a tripod and a candle model. So whether you measure here or here or here or here or here, the angles will be 109 degrees 28 minutes. Okay, that is a symmetrical molecule, and this is what we explain about the sp3 hybridization. Whenever carbon making the 4 sigma bonds, the hybridization obviously will be the sp3 hybridization. Now let's go to the another hybridization called second one, sp2 hybridization. sp2 hybrid, the best and smallest example. Complicated examples we can see later, but the best and the small example is ethylene molecule. By taking, you can explain this hybridization, in which in the excited state already we noticed 1s2, leave it, 2s1, 2px1, 2py1, 2pz1. Out of that, only 3 undergoing the hybridization. Because why you are doing like this means, if you carefully see, the carbon once again making the 4 bonds, but 3 are direct bonds. This bond, second bond, is called pi bond, so which is a anhybrid electron. So leave the 1 electron as it is and show the hybridization. Only these 3 are undergoing the process called mixing. So how many hybrid orbitals are formed? Only 3. That name is sp2 hybrid, and each one will be like a small lobe and a big lobe. 3 hybrid orbitals already I described. They takes place in the trigonal planar shape. So 3 sides 3 will be there. With reference to the plane of this one anhybrid orbital, that is a long shape, a pz orbital will be dumbbell shape. So half of the lobe will be above the plane, half of the lobe will be below the plane to this one. It is connected to this the carbon atom. So the carbon atom will have 3 sp2 orbitals, and this is what pz anhybrid orbital, sp2, sp2 and sp2, 3 sp2 orbitals, which are equal in the energetically and the shapes and all that. They are small lobe, big lobe, together with 1 hybrid orbital. So how many orbitals are written here means, leaving the 1s2 orbital, 3 hybrid orbitals are shown. These 3 are merged up, formed into the sp2 hybrid orbital. This is pz orbital. Now to explain this, I have to take the 2 such carbons, carbon 1 having the sp2 hybrid orbitals, 3 sp2 hybrid orbitals, and again carbon 2 also is having another sp2 orbital. So sp2 and sp2 making the 1 sigma bond, that is strong overlapping always leads to give the strong bond. This bond is called sigma bond formation. Just like here all are sigma bonds. Now the between the carbon 1 and carbon 2 1 sigma bond is formed. Remaining 2 sp2 orbitals, if they are allowed with the hydrogens, we have a this side 2, that side 2 hydrogens. Now at this carbon we have 1 pz orbital, here also 1 pz orbital. Now the entire this 6 orbitals will be in one plane. With reference to the plane of this molecule, two hybrid that is unhybrid pz orbital, they are parallel to each other. They actually strictly cannot overlap, but they go on bend, and between these two unhybrid pz orbitals we have a bond formation. This is because of the lateral or sidewise overlap. Two overlaps makes only one bond, the two weak bond than the sigma bond. So this overlapping results in the bond formation called pi bond. That's why I have written two bonds, but these two are not identical. One is sigma bond because of the hybrid orbitals overlapping. They are end to end. So more strong overlapping always is designated as a sigma bond. These bonds are actually parallel to each other. They cannot meet actually, but they slowly go on bend like this and will have a sidewise above and below overlapping, making a weak bond called pi bond. So there are totally carbon making 3 sigma bonds, and here also 3 sigma bonds, and this is what the pi bond. So totally we have 3 plus 2, 5 sigma bonds and 1 pi bond. At each carbon the symmetry will be trigonal planar. Entire molecule is said to be planar because the trigone of this carbon will be in the same plane with the trigone of this carbon. So the pi bond will be above the plane and below the plane will be there. With reference to the plane, at the plane of this one, the pi bonded electron density will be 0, nodal plane. So the above and below pi bond will be there, and in the plane, so these 5 bonds will be there. Sigma bond between the carbon and other 4 sigma bonds of the hydrogen. What is the shape of the molecule means planar. At every carbon 1 and carbon 2 will have a trigonal planar symmetry. With reference to the 3 hybrid orbitals, the shape is defined. If the carbon is asked, shape trigonal planar. The angle will be here 120, here 120, even between the 2 hydrogens also will be 120. The entire molecule shape will be the planar, right. So whenever carbon makes a 3 sigma bonds and 1 pi bond, it will be sp2 hybridization. Now similarly, we have one more hybridization called sp hybridization. The best example for this one is carbon with triple bond carbon and hydrogen. Systematically it is called ethine, or commonly known as acetylene. Acetylene is a non-IUPAC or the common name. Systematically called 2 carbons eth, a triple bond ine ending with e, ethine. No other functional group, therefore ethine. If OH is there, we can say ol ending, but here there is no other functional group, therefore ethine. So let us see how the bonding is there, what type of bonding means. You try to understand this single bond is always sigma bond, that is a total overlapping. But out of the 3 bonds, only one is sigma bond, the other 2 are pi bonds. That means this carbon makes only 2 sigma bonds. Sigma bonds are hybridized. 2 sigma means 2 hybridized means s and p orbital. 1 s electron, 1 p orbital is going to hybridize. Remaining 2 electrons, that is unhybrid electrons, are going to make the pi bonds. Unless you know the structure of the carbon that is bonding in the particular molecule, you cannot propose the hybridization. So this in the excited state we have 1s2, 2s1, 2px1, 2py1, 2pz1. Out of these 4 electrons, 2 are going to make the pi bonds. So leave these 2 orbitals for the pi bonds formation. They are not going to participate in the mixing process called hybridization. Only 2s1, 2px1 are going to make bond formation, that is hybridization, and the hybridization is called s and p, sp hybridization. And how many orbitals? 2 hybrid orbitals are formed. They are called sp hybrid orbitals, and each hybrid orbital will be like this. So there are 2 hybrid orbitals are there. And how that carbon after the hybridization looks means a carbon with 2 sp hybrid orbitals, each will be dumbbell and that is spherically dumbbell and facing one opposite to the other one, making a linear structure with the 180-degree separation. What about these anhybrid orbitals? They will be not mixing with the s orbital. Therefore, with reference to the x-axis, these hybrid orbitals are placed in a linear pattern. With reference to the x-axis, on the y-axis there is one anhybrid py orbital, and there is another z-axis like this. With reference to the x and y, the z orbital will be perpendicular to the x as well as y. So, you cannot write on the board. Actually, the board is two dimensional, but the z axis comes like this. So, therefore, I draw an imaginary line. On that imaginary line, this is called the z axis, an imaginary line on which the pz orbital I am writing. So, these two are the anhybrid orbitals of py and pz, these two, and these two are hybrid orbitals of the sp hybrid. Now, to show this bond formation, first show the carbon 1, carbon 2 with a sigma bond formation first. sp hybridized makes a end on overlapping, making one sigma bond formation. Another sp orbital, let us allow with the hydrogen, makes one more sigma. This side also one sp versus one hydrogen, another sigma. Now, at this carbon, sigma bonds are exhausted. So, remaining now the pz orbitals. First, let us overlap py versus py, and above and below, just like in the double bond formation. So, one pi bond is formed because of the py. Now, the pz orbitals are again they are parallel to each other, but they come front side and the back side. They may be written like this. Now, the figure has become little shabby, but one has to understand that the py are parallel, pz also parallel, making one more pi bond. So, two pi bonds and one sigma bond is represented as a triple bond. In this triple bond, either one you can say one as a sigma, the rest two are the pi bonds. Now, the bond angle between the bond and bond is 180 degrees. This hydrogen, carbon, hydrogen all comes into a line. So, the shape of the molecule is described as a line or linear model. Okay? The shape of the acetylene is linear. Two hydrogens and two carbons come into the single line. So, the making the 180 bond angles. Here the carbon is showing the sp hybridization. Hydrogen it is using its 1s1 orbital. So, whenever carbon makes a triple bond or two sigma bonds and attached with the carbon two pi bonds is now the sp hybridization. So, simple examples we have taken methane and ethylene and acetylene for this hybridization. Now, let us take some little more examples or little complicated examples for the sp3 and sp2 and sp. It is not necessary in a given molecule both the atoms should have sp, because hybridization is a concern of that particular carbon. So, first carbon may be sp3, second carbon may be sp2, side by carbon may be sp, and so on also. So, like that we take some more examples. Let us discuss what type of hybridization. Let us take one molecule like CH3C with the double bond CH2. I have written the molecule like this. Here the carbon is making the 4 sigma bonds, 3 with the hydrogens, 1 with the carbon. 4 sigma means all are hybridized. So, 4 electrons available with the carbon exhausted in the hybridization means S plus 3 p orbital. So, this carbon will be always. So, you can make a chart like this. Whenever 4 sigma bonds are there, hybridization will be inevitably it will be sp3 hybridization. When 3 sigma bonds are there making carbon, it will be sp2 hybridization. When 2 sigma bonds it is making means sp hybridization. You can follow this type of the small chart also, but this carbon is making here 1 sigma with the carbon 3. So, this carbon is having the sp3 hybridization. whereas next by carbon we have here 3 sigma bonds and 1 pi. So, it is having sp2 hybridization. This carbon is also out of 2 bonds 1 sigma with the 2 hydrogens 2 sigma. So, that is 3 sigma means again sp2 hybridization. So, 2 carbons are sp2, 1 is sp3. What will be the shape of the molecule means entire molecule shape you may not exactly you can say. At this carbon it will have a tetrahedral shape, at this carbon it will have a trigonal planar shape, at this carbon again trigonal planar shape. So, the molecule will have a total molecule shape you may not explain, but at this particular carbon what will be the shape of that carbon will be, or the part of the molecule will be tetrahedral structure will be there. So, the angles also at this carbon all the band angles will be 109 degrees. At this carbon though it is written looks like 90, but this what looks like what I am writing on the board is not the criteria. Hybridization will decide the bond angle. It is sp2, therefore, at this carbon it will be 120, 120, 120. Really speaking, the carbon will have 3 sides, 3 bonds. This is double bond, let us say. So, I think we are doing little justice like 120, all the angles are 120. At this carbon we have a now 109 degrees hydrogens, right. This may be the little closer representation of the original structure of the molecule. So, at this stage it looks like it is 90, but it is not 90, it is 120 degrees, 121. Wherever sp2 carbon it is 120 degrees and the hybridization will be like this. So, here we have a 2 different varieties. Similarly, a carbon with a double bond and a carbon again with a triple bond. So, here the 3 hydrogens, here 1 hydrogen, 1 hydrogen, here 1 hydrogen. So, the molecule if it is given at this it is sp hybridization, here sp hybridization, sp2 hybridization. Count the sigma bonds and then immediately you can identify all 4 sigma, they are all hybridized. So, how many hybridized? 4. How the carbon makes 4 hybridized S and P3. So, therefore, 3 are hybridized S and P2, they are undergone S and P2 undergone hybridization. So, how many sigma? Only 2 sigma, that means 2 are hybridized. 2 are hybridized means S and P, therefore, sp hybridization. So, never go by the triple bond, double bond, single bond, that is wrong concept. For example, if this is the molecule we have, the middle carbon is only having the double bonds, but how many sigma bonds it is making? This is 1 sigma, 1 pi, 1 sigma and 1 pi. So, this carbon making only 2 sigma bonds. 2 sigma means 2 hybridized. What is the hybridization? S and P. These 2 pi bonds are 1 p orbital, px making, py making one side, pz making one side. So, these 2 pi bonds will be, one is py, one is pz. Therefore, the pi bonds are perpendicular to each other. This pi bond is perpendicular to this pi bond because of the one is py, one is pz, isn't it? Now, this is 2 sigma means it is middle carbon is sp hybridization. See, we think that only the triple bonded carbons will be sp. No, here a carbon with 2, this carbon is 2 sigma, 2 pi, isn't it? Same side. So, here also 2 sigma, 1 pi this side, 1 pi that side, 2 sigma, 2 pi. So, that is 2 sigma. Never go for the, that is by based on the how many pi bonds, based on how many sigma bonds. Sigma bonds are nothing but the hybrid. How many hybrid? 2. So, what combination? S and P, therefore, sp hybridized. However, these last 2 terminals are sp2 hybridization. Like this, count the sigma bonds and how many sigma bonds are there, corresponding will be the hybridization. Now, let us take another concept, that hybridization in charged or intermediate species like. A molecule like, for example, if a methyl chloride is taken, right. If this molecule originally the carbon is sp3 hybridization, but if it cuts here like this, the 2 electrons will be taken away by the Cl only. So, one hybrid electron used in this will go with the carbon only. So, So, this carbon will have now result in the formation of a positive charge. Cl will become into plus, however. So, only 3 hydrogens will be there and there is a carbo, the carbon will acquire a positive charge. Now, such a type of the carbon is called, this group is called methyl. A carbon with positive charge is called carbocation. Carbocation. In this carbocation, originally we have 1s2, leave it, okay, 2s1, 2px1, 2py1, 2pz1, right. So, out of this, one electron is being removed, only these 3 are available. So, what will be the electronic configuration of this one means 1s2, 2px1, 2py1, 2pz1, leave it, 2s1, okay, 2px1, 2pz0 will be there, no electron, because the last electron is taken away by the chlorine. So, therefore, 2pz will be 0. So, how many orbitals are going to make the hybridization means available electrons only undergo sp2 hybridization. So, 3 sites 3 hybrid orbitals will be there like this, and they, if they are allowed with the hydrogen, 3 sites 3 hydrogens. What about this pz? With reference to this plane, half lobe will be above and below. This is a vacant, right, vacant unhybridized 2pz orbital, 0. No electron will be there. This is a vacant orbital, that is why it can take electrons, acts as electrophile. These 3 are hybridized, the angle between the any 2 of the hydrogens will be trigonal planarity. So, therefore, 120 degrees will be there, all the hydrogens will be identical. In fact, the symmetry of the carbon will be 3 sides 3 hydrogens will be there, and it is sp2, therefore, trigonal planar, a positive charge will be there on the carbon, right. This is what, whenever the carbon gets this type of the positive charge, when 3 sigma bonds are there, a positive charge will be there, 3 sigma will be sp2, already we have seen in the chart also. Now, the one vacant orbital because of the loss of the 1 electron. In sometimes what happens, if a methane molecule, in the other case, if this H goes out as a H plus, leaving the electron to the carbon only, then this carbon results in the formation of the CH3 minus. Such a type of this species is called methyl carbanion. Methyl carbanion. Now, what will be the symmetry means 1 electron is added. So, added electron goes to the S2. So, 1s2 will be intact, but the 2s will become 2, 1 electron is added. So, 2px1, 2py1, 2pz1. Now, the how many bonds it is making means, how many bonds means 3 bonds it is making. These 3 electrons will participate in the bond formation. This resides as a hybridized, but it is a pair. So, all the 4 undergo hybridization and the 4 hybrid orbitals are formed. Out of the 4 orbitals, one will have a 2 electrons, the other 3 will have a 1 electron, right. So, these 3 will make the bond formation, this pair will be there. So, the shape will be, because of the pair, as per the Westport theory, slightly distorted tetrahedral shape will be there. The hydrogens may come little closer because of the repulsion between the lone pair and the bond pair. So, these 3 will be bonds formation with the hydrogens. So, what will be the hybridization means, sp3 hybridization will be there, but these 2 electrons will be there in the a hybrid orbital. This is not a S2, it is a sp3 hybridized orbital. sp3 hybridized orbital, one of the hybrid orbital will have a pair of electrons, the other 3 will have a 1 electron, sp3 hybrid orbitals making 3 sigma bonds. The angle is not like 120 here. With reference to the lone pair, it is tetrahedral shape. So, therefore, approximately 109 will be there, but because of the Westport theory, the lone pair repulsion, the hydrogens may come little closer, and the exact symmetry you may describe as a slightly distorted or disturbed tetrahedral shape will be there, not the trigonal planar, because it is a pair will be there. So, it is similar to the tetrahedral symmetry. Even free radical also, if the bond breaks like this, one electron that side, one electron this side. This results in the formation of a CH3 dot. Even the dot undergoes a sp3 hybridization, rarely sp2 also explained, but if all the electrons, even that one electron, this one electron, no loss, no gain, all will have one electron, therefore all will undergo sp3 hybridization. So the free radical, this one electron containing species is called methyl free radical, methyl free radical. The free radical also will have the sp3 hybridization. There are two more slightly less asked, but it is slightly difficult to understand also. For example, if a chloroform is there, they are also intermediate. This chloroform, when it is treated with the potassium hydroxide, right, the OH minus will take away the H plus, leaving the pair to the carbon only. Leaving the pair to the carbon only, only H plus is taken away by the OH minus, so water is formed. And this K plus will take the Cl with 2 electrons, that is taken away. So therefore KCl is formed as another product. So what remains is now the carbon with one side electron is gone, so there is a vacant orbital, one side electron is given, so therefore it becomes a pair. So one pair is there, one vacant orbital is there. This type of the species, if these two are hydrogens, you may represent CH2. Okay, the 2 electrons in one pair only, so therefore they are shown as a paired electrons. They are in the same orbital, so therefore they are represented like this: CH2 with one up, one down, or CH2 with a pair and a box. Okay, a pair and a box may be shown. If there are this CH2 is called methylene. So how do you call this one? Dichloromethylene. And the system of containing this one box and one pair is called carbene. And that too it is called if these 2 chlorines are there, dichloromethylene, and it is both are in one pair, it is called singlet. Dichloromethylene are the substituted groups are there. If it is only CH2, you can say methylene, but because 2 chlorines are there, so dichloro singlet methylene carbene, dichloro singlet methylene carbene. Now what will be the symmetry of this one means? So the electronic configuration of this one will be 1s2, leave it, 2s1, 2px1, 2py1, 2pz1 is the original electronic configuration. One electron is added, therefore this will become 2. One electron is taken away, so therefore this will become 0. So this is the electronic configuration in which it is making 2 sigma bonds. So definitely these 2 will be involved in the hybridization, always pair also involved. So hybridization will be sp2 hybridization. So 3 sides, 3 orbitals will be there. One will have a pair, okay. Another one will be one electron used in the either in the chlorine or in the hydrogen. If nothing is there, you can say hydrogen, and one pz will be with reference to this trigonal planar shape. One pz will be there, vacant orbital. This is pz orbital. This is hybrid sp2 hybrid orbital in which a pair of electrons are there. So it has a pair to donate, so it can act as a nucleophile. It has a vacant orbital to accept, it can act as an electrophile. It is amphiphile, in fact electrophile and the nucleophilic nature will be there. It's a very transit intermediate state. However, many times what happens, if this is formed, let us say in a reaction, immediately what happens after some time, one electron will jump into here and then you will get 2 hydrogens with 2 free radicals. This is called another intermediate called triplet intermediate. In this triplet intermediate, the 2 unpaired electrons are there. The electronic configuration will be 1s2 will be there, 2s1, 2px1, 2py1, 2pz1. No loss, no gain. All the 4 electrons are there, but different. They may be represented like this. One up and also up. That means they are in the separate orbitals. The spin is not paired, isn't it? So you will have now this type of hybridization, of which 2 are that is left free, only 2 are undergoing the hybridization. So, sp hybridization. So, in the sp hybridization, one will be this side, one will be that side. These 2 are hybrid orbitals with reference to the x axis, they are on the line. What about the py? Py will be anhybrid py, okay, with reference to the x axis, they will be perpendicular. Pz will be like this, another the anhybrid orbital pz. So, the 2 electrons will be anhybrid electrons, and these 2 are hybrid orbitals. And what will be the angle between 2 hydrogens? Means it is linear shape, therefore 180 degrees will be there. This is called triplet methylene carbene. CH2 is called ordinary methylene. If chlorines are there, dichloromethylene carbene. The singlet always changes to triplet, that shows singlet is less stable and the triplet is more stable. Always in the sp, S percentage is more. As the S percentage is more, overlapping will be more, stronger bonds and stability increases. Therefore, sp2 hybridization changes to sp hybridization by shifting 1 electron from pair to the box, and as the time passes, the singlet methylene carbene changes into the triplet methylene carbene. So, these 2 also in intermediate species. Just carbocation, we have sp2 hybridization, carbanion sp3 hybridization, free radical sp3 or sp2 ambiguity are both are possible, and this a singlet carbene will have sp2 hybridization, triplet will have a sp hybridization. As per the little complicated molecule, for example, a CH with a carbocation is there, right. Now, discuss the hybridization on the terminal carbon. For example, if this is given, this is a neutral carbon, all 4 sigma, so sp3 hybridization, okay, clear. 3 sigma 1 pi sp2 hybridization. Discuss about this carbon means this carbon has only 2 sigma bonds, 1 pi bond, 2 sigma and 1 pi bond. Leave the pi bonds and all that. Sigma bonds how many? 2. So, hybrid also 2. Whenever lone pair is there, you have to consider that as a hybrid one. If it is vacant orbital or positive charge is there, leave it only sigma bonds, so 2 sigma, so sp hybridization. Okay. So, this is sp hybridization based on the 2 sigma bonds. 2 sigma means 2 hybridized. What is the combination? S and P. Therefore, sp hybridization, 3 sigma sp2 hybridization, 4 sigma sp3 hybridization. Whenever pair is there, pair should be considered as a one of the hybrid bond. Always pairs will be inside like this. This is a pair. So, it should be participated. Otherwise, leaving the S, how P undergo hybridization? P both are double. Again, double only will come. Whenever you get a small lobe and big lobe, that big lobe participate in the bond formation. Therefore, the strength of the bond overlapping increases. Therefore, it is inevitably always, is there any pair if it is there in the s orbital, it should be participated. That side, if it is vacant orbital or pi bond formation electrons, you can leave it, but this side you cannot leave it. So, sp2 hybridization involves these 2. It is the actually 4 electrons, but orbitals are 3 only. So, hybridization takes place only in the orbitals, not in between the electrons. Electrons are nothing but orbitals, no doubt, but 3 orbitals are involved. So, 3 hybrid orbitals will be formed, having the 2 electrons, 1 electron, 1 electron. Okay, right.